Yes. Wow. Thanks for that introduction. Of course, thanks to the organizers. As with Veep, I'll very quickly give you an excuse for why I should appear here. Of course, I come to hear some very nice talks. Thanks. But I haven't known Core nor Karma as long as Veep has. I'm, of course, much younger as part of the reason, by the way. But I have deeply enjoyed years and years of collaboration and personal and professional interactions. And, there's something fantastic about what we do. And I hope very strongly that it continues. I have to say that. Okay, but I should do the stuff because I like to forget the other things. So I'm going to talk about a question that came up in our work. And well, I'll try and go through it in a reasonable order. So I'll wish to tell you about what we did with Carrie Calta of Vassar College on Core. The idea is to create certain extensions. There's a conjecture that came up. I'll tell you about how one might want to think about it and then sketch a final proof. So let's see how it goes. So first of all, Hitoshi said that a continued fraction is something where there's a map, something goes to 1 over, z goes to 1 over, or possibly minus 1 over z. I want to relax it just a little bit. I'm going to have a group, in this case, a group of index 3 and infinity. Standard continued fractions are related to a group of 2, 3, infinity. So let's start with the infinity. It sounded big, but it's just that. We have a cusp, we have a translation. Of a translation of, in our situation, t, and t has whatever value is written there. Okay? And in the traditional situation, t is 1. Then the 2 is what gets us x goes to minus 1 over x in the standard situation. And we're going to replace this by, today it's 3 and infinity. So I'm going to concentrate on the element of order 3. And drop the other one. And so there are, of course, numeric values. These are all algebraic numbers and nice things like that. And so we're going to say what we want to do is inspired by a beautiful work by Hitoshi Nakada on his, many people call Nakada alpha continued fractions. And the idea is we'll just take any window of width or translation length. We'll apply what we wish to get out of there. And we just pull back in with the translation. As simple as could be, and I think that Core already said, we thought this would be a quick and easy little cute thing to do on a plane or something. So, and it is simple and easy, right? I repeat, we've got this C that's acting as a rotation, and one proves that, for every x in our chosen interval of length t, that some finite number of applications of C takes us out, and then we translate back in. And in this case, it's either 1 or 2 because of that 3 and the 3 and infinity. One can play the game with more groups. There's, of course, just a little form. Whoa. So, and we get some interval maps. There's a parameter alpha involved. It's going from, say, 0 up to 1, this orientation. And so on the left-hand side, the 0, greater than 0, it looks pretty nice. This is in the region where we apply our rotation once and we're out and pull it back in. It was pretty simple. As we move over, look, there's some sort of phase change, and suddenly some x's demand that you apply that C twice. They want to hang out for a while. And so the dynamics get surprisingly complicated. So we were happy to prove that we could find nice ergodicity results, ergodic measures. We were really starting to ask about, in parallel to what was known about Nakada's alpha continued fraction, that much of the game is controlled by what he and Natsui really pointed to was the matching intervals. So as soon as, when it happens, perhaps I'll say, for your map, that the right and the left endpoints in their orbits eventually match, and then continue to be the same. If that holds on an interval, then it wouldn't be so surprising. You can really control the dynamics on that interval very explicitly. That runs a lot of the game when one looks deeply into those continued fractions. In particular, a question that was around for a while was the continuity of entropy there. So that was proved for the alpha continued fractions in 2012 by Tiozzo and a team, and Gore and some other people. And then, let's see what happens. And now let me tell you a little bit how one proves such results. It's very hard to work with these infinitely branched functions, so the idea is to move up to a natural extension, right? You're applying the function, you're losing the past. You don't want to lose the past, so you create something that grabs it. That's our natural extensions. And so we're going to build them very naively. So these maps are simple. They're given piecewise by a linear fractional transformation M. So I partition the given interval, and I have for each little partition element a corresponding matrix M, and X is sent to M on X, AX plus B over CX plus D. M is determinant 1. And then we want to do something nice to keep track of the second coordinate. In this case, I'll just conjugate by this element of order 2 projectively. Nice thing is here we get a very nice looking, I suppose, invariant measure. Notice I've taken different coordinates than Hitoshi likes to use these days, but he used to use these. And so what happens now? Now we also run some computer and we see the truth. Except, of course, it's some finite representation of the truth. And so what we see is I've taken the function that I graphed on the left, and here is the system that I've given you with piecewise given by the action of M and the conjugation on the y's. And what's very nice about the system on the left is the action of this two-dimensional system sends rectangles to rectangles. It's very easy to follow what's going on. But some people like Lebesgue measure, and there's a conjugate system that has Lebesgue measure as an invariant measure. It's quite nice, obviously. And so the goal is often to prove that this domain that has presented itself by taking some generic point for the system and plotting its orbit for a long time. Of course, that's a little bit of a problem already. It's so hard to find normal numbers. But as Pierre was showing us with the flow, these machines are actually great for this because sooner or later it gets introduced, and so these are usually quite accurate. And so now what happens, I'll say briefly, on these matching intervals, what happens is that the heights of my rectangles turn out to be certain algebraic numbers, and then you come along with such a matching interval, and the rectangles of the various heights, these are moving. Then you reach the end. Let's look at that top little piece. You can imagine I come on a matching interval. As I move along, that little piece keeps moving over to the right, and once it goes and disappears, new game, it turns out. I'm at the end of a matching interval, and then I look, and if I'm in the alpha continued fraction, then there's another matching interval, and then another, and it cascades. It's beautiful, and it comes down to a limit that's a transcendental number. But in our setting, it's different, but there's a tree that tells us where to go to follow matching intervals. It's sort of interesting. So that was all fun. So we proved some of these things over, Gore already said, some surprisingly high number of years, I suppose, given the fact that we are in the easy case, by the way. So then the next set of questions, sort of after doing this, is, well, is it the case that this very simple continued fraction, very natural system, right? We just rotate it out, translate it back in. Shouldn't this really be coming naturally from the group? And the natural way for continued fractions to come from a group is that there's a flow on the unit tangent bundle. You take a two-dimensional section, that's like the pictures I've been showing, these two-dimensional ones, and there's a factor map. It's a projection map down to the interval, and our little interval map has really come from that return map to the cross-section, which is part of the flow in our three-dimensional unit tangent bundle. That's actually the natural thing. It's completely geometric. So we would like that to hold here, but the methods I learned from another long-time co-author, Pierre Arnoux, are such that I know they do not work immediately because these maps are in general not expansive. You need to have an expansive map. Ha! No problem. We proved that all these maps are eventually expansive. So I can hope for it to work. But I've got an upcoming problem. It's that, and I should have said more before this, it's that the way things are set up, I'm going to find that I have a return map once I do this fix of the, once I go, let's say, to the, eventually, I just take the compositional power and get the expansive power. What happens is I want the first return. And that turns out to be slightly delicate, but easily explained. So let me explain some of this. I had another thing on the slide. Who knew? So if I had deciphered all that more clearly, you would be more convinced that, it's reasonable that we're going to get virtually what we started with, coming up naturally geometrically, if and only if the entropy, measure theoretic entropy, times the size of our domain is always equal to the volume of the unit tangent bundle. And so I'm going to sketch why that's reasonable. If I had a great memory, I'd know whether that's the next thing coming up. Yes, I'm going to go right back to the basics and start again. Okay, so it's been fun to watch other people use the blackboard as well. Also, I've noticed they're hard to move. So, beautiful picture. SL2R acts on unit tangent vectors on the upper half plane. So this is the upper half plane H. And the shortest paths, the geodesics, are either vertical lines or they're perfect circles as drawn with center on the real line. And what happens is a unit tangent vector has a base point, and then it has a direction. And it says head this away, clearly. Right? And then you might give me such a unit tangent vector, say here, and it lights up exactly one geodesic. And now the geodesic flow is, you give me, so let's call this U for unit tangent vector. You give me a positive for my e's first, real number, and we're going to flow along the geodesic announced by the unit tangent vector for arc length t. And then we found the base point, but we have our little circle, and so we know what the tangent vector is right there. And so this is the beginning of the geodesic flow in the unit tangent bundle. So in the upper half plane, it is, with all due respect, somewhat boring. Right? We just follow along. Of course, t could be negative, and so what do? We keep the orientation of u and just slide back. Right? All these things, great. And now what happens is I apply some matrix, and I will find that the base points, I'm ready again. As I wrote, SO2R acts transitively. I can send my chosen unit tangent vector to y this u. I could construct the element of SO2R that does it. That's a transitive action. We should mod out by a stabilizer of our chosen guy. That's just plus or minus the identity. And so we get that PSO2R is exactly the unit tangent bundle of the upper half plane. And the geodesic flow is, I simply multiply by, on the right, by a matrix that moves my chosen vector up arc length t, and then when I apply m, all these m's are isometries, orientation preserving isometries. My little up goes right over here by the m, and so I really can just rewrite things in a very simplistic manner. What I learned from Pierre years ago, he told me this. He had a factorization, basically, a way to just put pretty general matrices. There are about 4 different ways to do this. Let's do it in the setting where gamma is positive. So I have alpha, beta, gamma, delta. And then you can check that we can surely find a value of t so that we can factor this given matrix with gamma greater than 1 as a of xy times g of t. We're going to think of the collection of those a of xy's as a transversal, and we're going to move with them through the various geodesics. Okay? We're going to follow the geodesic from each of those. Again, on the upper half plane, cute, but not so useful. But there's another step. So these coordinates are such that the natural measure to be using on the unit tangent bundle here is some reasonable hyperbolic related measure. And then we've got an S1 of directions at each point. For me, that's complicated. I prefer Lebesgue this time around. Right, so it's a very nice recoordination. Well, I'll get the word later. And so now I want to go back to continued fractions since I have so much time. And what I'll do is I recall that t of x is given by m acting on some x. And I like this in the first coordinate. So you give me the matrix M now A, B, C, D, which affects my t of x. And I will start out by the corresponding capital A of xy. And now we simply find the right flow value to come back to this transversal, but now with m of x and the correct y value for it. This, of course, the story is we have determinant 1. And if memory serves correctly, Pierre wrote this such equations in his talk a couple days ago. So now, as I said, the upper half plane is always interesting, I suppose, but now I want to have a group acting such as my group of index 3n infinity. I mod out by the action of this group. The group acts fantastically nicely. And so if this were the modular group, we saw that we would have the modular surface. We saw this quickly sketched because this controls all lattices, integral lattices, etc. And now what happens is geodesics can look much more interesting in general. And in this kind of situation, what we have is that the geodesic flow with respect to the natural measure, which is the projected of the natural measure, is ergodic by results of Hopf in the 1930s, which were motivated by early results using continued fractions to track geodesics on the modular surface. And so what happens in this situation is, so we have our map, x goes to mx. We've built the planar two-dimensional region, and now we'll take for each x and y, we have a of xy sitting inside the unit tangent bundle, and now we are given m, we can solve for, that's a square bracket on the other one, and so these mean equivalence classes because they're orbits under the action upstairs. So these are point unit tangent vectors on the quotient surface. And so we're flowing on the unit tangent bundle of the quotient surface, and that flow brings us back to our copy of the planar region that's sitting in there. Right, so I start up with my little planar region. I now know that these are actually unit tangent vectors. Announces a flow. I flow for the time that m told me. But m might not have told me the first return time. M was part of the definition of the function. Right? The function was just defined. The question is, did I use the right matrix in order to return the first time? And the answer is, I already know no, because there are negative return times. On the non-expansive branch, it goes the wrong way. It points this way, but it moves backwards. And that is not positive time flow, and that's what we really mean when we say first return. We flow positive time and come back the first time to the section. So Pierre had explained these ideas to me some large number of years ago, and then in the setting of the alpha continued fractions, it was proven that the measure theoretic entropy times mu of omega was a constant, and that constant for alpha equals that's called 1, alpha equals 1, was known to be the volume of the unit tangent bundle of the modular surface. And so the question was it true for all of these, that all of the alpha continued fractions are given as factors of first return maps to sections of the unit tangent bundle? The answer is yes, and it's because of Pierre's cross section is transversal. We proved it slightly differently. I think this is clearer for it. So these maps are so nice that the measure theoretic entropy can be simply calculated using Rocklin's formula. So we integrate over the interval of definition, the log of the derivative. These are yes, smooth enough everywhere, and against the invariant measure. Well, the invariant measure is coming up. I see the next line is, but at each step, this is applying m dot x, and this is x goes to ax plus b over cx plus d of derivative cx plus d to the minus 2, if I could say all that. And I take a log, the minus 2 comes out, and I see this log of absolute value of cx plus d. That looks great. Now, the invariant measure we find is the marginal measure. It was already mentioned a couple of times. So in our interval, we take any, say, Borel set, and we simply look at the fibers above it in the two-dimensional situation. We apply the two-dimensional measure, and that's what we assign and get ourselves nu. Oh, I want a probability measure. And so I can integrate over omega against that d mu that I just mentioned. So it's a probability measure. So, of course, I have to mod out by the mass of that two-dimensional domain omega. So, and then finally what happens is, well, we tuck everything into the unit tangent bundle. We're flowing along, and we know that we come back because this diagram was commutative in the right way. But as I said, this is in the expansive, everywhere expansive situation, determinant 1. As I said, actually what happens is, and we've given examples of this, that the given map is such that you actually come back with various return times and not the first return time. But let's just take the set of the geodesics we see. That whole set is flow invariant. We flowed, and we just keep following the geodesics. It's flow invariant. It's very easy to show that it has measure bigger than 0. So by the classic Hopf result, we get the whole of the unit tangent bundle. And so what happens is we get the whole, this works out because of the measure that I showed you from Pierre also, that we get that we will equal, we'll have equality here exactly when we have first return always up to measure 0 in all these words, of course. So it's first return if and only if we have equality. In general, it's greater or equal to that. And in various settings, one's been able to show that equality did hold, and when it has the first return map, as I said, there are, if you will, pathological examples. So now I want to quickly address that conjecture. The conjecture was that in our setting for this infinite collection, these are now GNs, right, that we have a way to fix our not being everywhere expansive. We simply, for every x, ready? It's an eventually expansive function. So there's some r such that t to the r is expansive. That means at every point, t to the r is expansive. That means every point sees a smallest integer, positive integer, such that t to that L, say, of x is expansive. And so we're going to take, instead of t to the r, we're going to take at each x, t to the L of x, the least number necessary. This is, yes. Yes. First of all, it's measurable, and then yes. So it partitions things very nicely. And so that's the map that we're trying to show is first return, because it's the natural fix, if you will, the most natural fix. And so what happens is that we prove that we just have to get the right equality at any alpha value. So there's some argument that obviously I should skip. Right? And so we can push all the way to alpha equals 1, and this is a situation where our two-dimensional domain looks something like this. We've got the square, and then we've got some rectangles that move away. They meet, this has infinite mass because of those red dots, if you will, and the angles, I learned. And then what happens, we already know that things work nicely in the Nakata case, and so what the Nakata case value gives us is that we know the value on the red square, and then the question is, what's the value that remains? And it turns out when you take off the volume that comes from the red square, it turns out the value is the volume from the Hecke groups. And so that suggests, it didn't suggest it to us quickly enough for the paper, that what we're going to try to do is, so we learned from the modular situation, this pi squared over 3, and then we want the Hecke value, if you will, on the remainder. And so what happens is, it turns out that in the Hecke case, there's a way to just shift from the true two-dimensional domain to the remainder piece of the domain in our situation. And so all I have to be sure is that that picks up the right volume integral. And of course, I wouldn't be here if that weren't the case. It does. It works just correctly. And then why does it really work correctly? This is a picture that Cora drew in the previous century. We looked at the Rosen continued fractions and to a beautiful result of Hitoshi, yet another beautiful result of Hitoshi Nakada. And so for these Rosen continued fractions, which are related to these Hecke groups, what he proved in this language was that the entropy, H times mu, is equal to 1/2 the volume. Of course, I got nervous. What? What's going on? I need equality. But what happens is we're in the easy case where every matrix is of determinant 1. But even in traditional continued fractions, you know this is a problem that, in fact, there are -1s and 1s involved. So in the traditional, anytime you have the -1s, you actually have to take 2 copies of your natural extension in there. And so you make really a skew product of it. And so you flow, and then you have to switch over and flow. So that 2 goes away. Let me just skip exactly why. And so then it's a trivial calculation in the end. Well, there's a more, but I hear the bells. Thank you very much.